Hi, welcome to the Signal Path. In this episode, we're going to try and see if we can fix this GW Instek power supply. Now, the reason I'm interested in fixing this one is because this is a fairly high power unit. It goes up to over 1,000 watts, and I think it can go as much as 80 volts, up to 40 amps, depending on the range and so on. So it's a very good DC power supply. Now, this is obviously a switching power supply because it's not that big. For 1,000 watts, that's the only way to do this. But nonetheless, let's go ahead, take a look at it and see what happens. Now, I've already plugged it in, or rather, I'm plugging it right now. And when I do turn it on, I do hear it click, but there's nothing on the screen, so nothing's happening. So obviously something's gone wrong inside, but some part of it must be turning on because of the sound it makes. And indeed, you can hear that it is a switching power supply actually going on. So we have to take it apart and see what's going on the inside. Alright, let's go ahead and take a look inside. Now, before I take it apart, please respect the dangers of working with mains voltages and high energy density power supplies like this. This can be very dangerous and is of course unplugged right now. Look at the back terminals. This is very high current, obviously, because this can go up to 40 amps or so. So nice beefy connectors and a power connectors coming out. It's actually a very nice looking power supply. So I've taken the screws off. Let's go ahead and see what we get. Wow, look at that. That is an interesting design. So it looks like it is completely enclosed in PCB on all sides. Unusual. Clearly, there are 3 fans at the back, which unfortunately you cannot see, but these 3 fans are going to cool whatever's underneath these 3 different PCB sections. These top portions are clearly designed just simply for passing a large amount of current through these big planes and connecting them together, passing some digital signals around and some analog control signals around. Now, this portion here is clearly the control part, and this is connected to the front panel LCD and the buttons and everything. So whatever is going wrong, this either is not getting power or something's gone horribly wrong with it because nothing's showing up on the LCD in the front. Now, the advantage of having this wrapped in PCBs like this is you can create nice compartments which are totally separate and act as wind tunnels themselves, because each fan then blows air through each of these sections and can be independently controlled without thermal crosstalk across them. So it's an unusual design and a very compact design. This thing must be packed. Now, these 2 ends do not look the same. This is SW01P08A. This is 1P1A. So there's a difference between them. And you can, in fact, see there's a difference in this side of the power supply too. So yeah, this is a covered plastic, of course, because the case is hugging this. Nothing at the top, but they're spaced here. These are clipped together, and you can see connectors on each side. So this should be able to be pulled out. But unfortunately, when you pull them out, you can't run it. So this is a nightmare for servicing. Now, there's nothing in the service manual. There's nothing in there to tell you. I can see connected through here all the high current outputs across here. So these are in parallel. Interesting design. So here I have taken the power supply apart, and this allows us to understand and analyze it from the ground up and figure out how everything is connected to each other. As we would expect, the power supply is going to have a main backplane board, and this board is where all the other individual modules plug into, and this interconnects them, provides them with signal, and passes the different voltages between the boards. The output is taken from the top, and I'll show you that there's a bar of metal that goes across and then eventually reaches the output, which is here. These 2 pins that you see here, this is a sense voltage supposed to be tied to the output, and this connector here plugs into the main controller module that was sitting at the top over here. And that's how everything is connected. And at the same time, the other boards that you saw at the top with the ribbon cable going across connect all the controls of all the power supplies. It means that this is really made of 3 identical power supplies. Each of those power supplies is made of 2 boards, and you can see them lined up there at the back. And you can see also that the connectors are symmetric and they're in pairs of 2 across. And there's the fan connectors in there to control each of them individually. So the system is pretty straightforward. AC line comes in, filtering at the front there goes to the front switch. This switch has electronic trip built into it, and then that line voltage is then placed onto these connectors, this one and that one, and that allows the AC to go into the one of the 2 boards of each power supply, and that board seems to be primarily responsible for doing the main rectification. And there's some switching networks in there, soft start and so on, but it puts out the main rectified voltage, 360 volts or so here in the United States, onto the main bus, and that the other module that you plug into picks up that voltage, does the main DC-DC conversion, provides the main output of the power supply going to the back, which is taken from the top. So the architecture is now fairly clear. And because of the fact that it has 3 identical power supplies built into it, it's unlikely that all 3 power supplies are bad, which means we should be able to hopefully use them in mix and match them and find out the problem and help debug it this way. So for example, here is one of the boards that I was talking about. This board primarily handles the AC voltage. You can see the AC going over here. It has its own filters, and there's a relay here with a soft start. And that once that clicks in, then the main rectifier, which is over here, provides the high voltage output there. It's got some other switching and some other things in there. I'm not going to go into the details to figure out how it works until we find out exactly which of these modules is bad. Now this one would plug in, for instance, somewhere like here. Like so. I can plug it in there. There it is. And then the main power supply that is responsible for producing the output. Let me just pick one of these up just to show you. Here it is. Now this is going to have the main switching, the main output rectifiers. Here's the controller board on it, and from the top connectors there is how it connects to the main controller. And if I go ahead and flip this way, I should be able to plug it in here. And these 2 boards will then talk to each other through the backplane, but do not talk to the other boards at all. This becomes a fully self-sustaining and self-containing block there. And here's the outputs of it. You can see big terminals with a metal bar going across, connecting everything together. So this is how it's really made up. It's made up of 3 of these sections. Now, we should be able to plug them one at a time and test them and see how it works and whether they start up or not. Now the easiest place to start is obviously with these boards and see if they produce the rectified output, and if the soft start and everything starts properly, we can find out if there's a problem with one of these boards. Now if I look at it carefully, I notice that the controller that sits over here is going to be connected to the middle power supply. And I don't see how else this can be powered unless the middle power supply actually works. If the middle power supply is broken, this will not be powered. And perhaps that's the problem, and that's why I was hearing the different noises starting up, but I couldn't see anything on the display. So it could be that the middle power supply is what is the issue. So let's go ahead and plug in one at a time, and I can use my isolation transformer and run the rectifier board at a much lower voltage, so that I don't have to actually run it at 120 volts when I'm plugging it in there. I can run it at 30 volts, and it should be enough to actually give us a soft start and make some measurements. So first thing first, let's make sure that the voltage and the power actually gets into the modules themselves. So let me put this into measuring AC and DC voltages. So right now the switch is turned off, so I expect to see nothing coming out of this. And let me turn the switch on. And I still see nothing out of it. That's probably because I'm not plugging into the correct place. That should probably help if I plug it into the right place actually. Here we go. So it should be this one. There we go. There it is. So we are getting our 30 volts, which is what I have my isolation transformer connected to. This is a little difficult tool, but if I turn the switch off, yes, it does go away. So yes, we do have power on the first connector. Do we have power on the second connector? And we do. And the last connector, we do. So, okay, so we have power everywhere, and that's already a good start. It means I should be able to plug in the main rectifier into any of these slots and still be able to measure the voltage. So let's do that. Okay, so here's one of the boards. This is the board that used to be in this position, so it's not the middle power supply. And I should be able to turn it on and see some rectified voltage. So here's the output of it. If this is working, I should hear the click of the relay and a voltage. There you go. I heard a click, and there you go. Check it out. Minus 40 volts. I just have the connectors backwards, but there it is. So it is indeed doing what it's supposed to do. So it is very likely that this module is fully functional. Now I can go one at a time and see if they're all doing the same thing. And here's the board that used to be at the end, so I'm leaving the middle one for last. And by the way, the reason I chose 30 volts is because it's high enough to get a soft start to start and actually get this module beginning to do the rectifying. If I go lower than that, it wouldn't start. But if I go higher than that, it starts to become dangerous. So you have to find the right voltage for this application. So here we go. So I'm going to plug this one here and here. I'm going to turn this one on too. Oh, I heard a click. There it is, 40 volts. This one is also probably okay, and it behaves identical to the old one, which is a good sign. Okay, and here's the last one. This is the one that used to be in the middle. And let's go ahead and measure this one as well and turn it on. Aha! It didn't even make a noise. So it didn't start. There we go. That's already very promising. So this board was the board in the middle, and it did not go through the soft start cycle. So the relay did not click. If you look closely over here, the relay, I believe, is this one right here. So I wonder if there's something wrong with that system. So let's go ahead and take a look at this a little bit closer by itself under the camera, so we can do some reverse engineering and figure out what's wrong with it. So here's the unit that doesn't go through the soft start. Now I looked at it, doesn't seem to have any mechanical damage or any obvious burn marks or anything like that. I checked the rectifier is indeed correctly, it has all the diodes properly. I checked these devices here, they all seem fine, but somehow the relay doesn't start. So the main voltage comes through here, and there's some input filtering here, and there's some other voltage coming here. I haven't really traced that one yet. But then there is a bleed resistor going through some of the relay terminals, and on the other side, sorry, it's a little bit confusing from this direction. Here you go. So here's our main lines coming in from here and here. There's some goes across the choke over here. There is another one going across the choke over here. There's our bleed resistor terminals over here. You can see that we're feeding some of that through. The control terminal of the relay is this port and this one. And if the relay is turned on, the voltage will jump from here into here, which is on the other side of the board, and then enters the rest of the power supply module. So I checked with the multimeter, and it turns out that it never gets past the relay, and that's because the relay actually never clicks. And this relay is supposed to only click once briefly at the start, and once it clicks and closes the connection, then the power supply is on and the relay stays in that position until the capacitors are fully discharged again. Now when it turns on, there's a control circuitry over here which gets power from the bleeding resistor originally in order to turn the relay on, and if that doesn't happen, then obviously nothing will happen. So we have to figure out what is going on. So I'm going to go ahead and poke around and check to see if there's any of these components that are not functioning. I can do some very basic measurements. For example, let's try it. I actually haven't done this. Let's go ahead and see if the relay has some appropriate resistors associated with it. So let me get this into view. There it is. So I'm in a ohm meter setting here. So let's measure the terminals of the relay. We expect to see a certain resistance. Sorry, my angle is really bad here. What do we get here? There you go, 716 ohms. That sounds about right. So the relay definitely seems to be functioning. Like I said, I measured everything else. The terminals of the relay themselves are open. That would be between here and here. Yep, the relay is definitely open, and you can see this is definitely working if I touch them. So yes, the relay is there. The terminals, these connections are obviously working. So I'm going to have to dig around a little bit more carefully and find out what's going on and make some comparison. So the voltage coming in through the bleed resistor, let's see the bleed resistor, how big is the resistor? It's supposed to be 20 ohms. Let's make sure that. And oh, that is interesting. That was unexpected. These things normally don't fail. Huh, that is a little bit surprising. Really, the bleed resistor of all things? I wasn't expecting that to be the problem. I was going to look at all the solid state devices that were responsible for turning this on. No, indeed. Very interesting. So let's measure the resistor from a functioning board. Actually, you can see that I wrote OK at the back of this. You can barely see it. And these all have protective cover, so I haven't taken the protective cover off. But I should be able to measure the resistor from here as well. Sorry, my angle is really, really bad here. There you go. Let's see. And what do we get? There you go, 20 ohms. That's exactly what it should be. Well, if that's the case, I should be able to put a resistor in parallel with this one, the one that's broken, and it should soft start. That would be interesting to try. So let me just grab a resistor of equal value and just tap onto it and try it again in the main chassis. So I have tapped two wires over here, and we should be able to just connect this across another high power resistor. This is 25 ohms, but for the purposes of what we want to do, it should be just fine. So I can just tap it across here and across here, and we can leave this somewhere away from the rest of the circuit so it doesn't touch anything. I'll just put it over here, and we should be able to do the exact same thing. So I'm going to turn the isolation transformer on. Everything is powered off, and we can go ahead and try to do the voltage measurement once again. If I can get this multimeter back into view. There we go. There it is. We'll put it back onto voltage there and turn the backlight on so you can see it. All right, let's try again. Now you're not seeing the whole thing in view, but I'm going to turn it on, and hopefully it will click now, and hopefully it won't explode. I've already changed the trip current of my isolation transformer. In case something happens, it will trip it off, because this could have died due to some other failure. So let's go and turn it on. Ah, look at that. Isn't that exciting? So I did in fact hear it click. So the relay did go through the soft start condition and is now stable, and it's producing exactly the same voltage. And we can convince ourselves and do something that I do not recommend. We can increase the voltage of the isolation transformer and make sure that this indeed reaches the voltage it's supposed to. I'm going to try and hold everything steady here. And we go all the way to line voltage. Here's our 400 volts. So indeed it is working, and I should be able to turn it back off and do another soft start. There is, by the way, here is the danger of this power supply. I've turned it off. Look how long it takes for this voltage to disappear, because there's nothing bleeding it out. The other power supply is not installed. This voltage is going to be present on this power supply for a long time, even if you unplug it. Well, I was doing some visual inspection on the rest of the modules, and I found something. I didn't think it was going to be that easy to fix this power supply. Here we go. So I'll flip it over. Can you tell what the problem is? Well, of course, there has been some minor explosions here. So we have to take a closer look and see what has happened. So I've already removed that pin there, so we can flip this up and just tape it down to allow us to work in this area. There we go. So let's take a close look and see what is going on, and if we can figure out the role of this circuit and what could have gone wrong for that explosion to happen. Remember, we have no schematics. We're going to have to do this on the spot. I'm just looking at it for the first time here myself. So here are the two outputs that are the main outputs of this module. That's what goes to the output of the circuit itself. There you can see the screw terminals at the top there. Now these two outputs come from these two terminals here, which are choke inductors falling over to the other side here, and there's a huge bank of capacitors and regulators. So the entire DC voltage comes to this through this little bridge over here. Some control circuit up there. There's some part here for some kind of adjustment, perhaps maybe balancing these power supplies to each other. I have to take a look. So if you look over here, we have the same terminals come over here and go through this little jump over here. This is a fuse on the other side. There's a fuse right here, and that goes through this 3-terminal device. Now by the width of these lines, you should be able to immediately tell that this is some kind of a transistor, perhaps a MOSFET, because look how thin this line is. That's the gate control, and some source and the drain on the other side. Maybe this S is for the source. So we can see that the source is connected to a bank of resistors here, and these resistors on them, it says R220. So they're 0.22 ohms, so they're tiny. So you have 2 of them in parallel. There's actually room to put 3 of them. So 2 in parallel in series with 2 in parallel, so the whole thing is actually 0.22 ohms, just more current carrying capability. And then it goes to there, and there's some more series resistors here before we go to the output. Again, room for adding more. And so this is indeed sitting across the power supply output. So the 2 of the terminals of the transistor are directly across the output. That leaves more room for this to be some kind of a balancing or rapid discharge for the output. And then the gate is controlled partially by the voltage of the source itself, and as well as some control voltage that comes through here. Perhaps that's what this is adjusting. So the transistor itself is an IRF640, I think. It's a MOS device there, very small series resistance when it's on. And if this MOS device becomes a short circuit, if it burns out between the source and the drain, then you have the entire output voltage of this power supply dumped across the fuse and these 4 resistors. So it makes sense why the resistors would explode if there's a large voltage across them. Let's say this was 80 volts and you turn it on and somehow there's something this dies and it just blows these resistors out, which I'm surprised why the fuse is not dead, because I did measure the fuse just now and the fuse seemed to be fine. I'm going to put this on just to measure it one more time. Hopefully you can hear it. Yep, as you can see, the fuse indeed there, but these resistors, they are gone. They have been vaporized. Yep, they're all dead. That's quite amazing how uniformly they all exploded. It's really interesting. Now let's try the transistor itself. Oh yeah, that's a short, that's a short, and that's a short. So all 3 terminals of this transistor are shorted to each other. So obviously nothing's going to work. I hope that this short over here did not blow out some circuit here. There is some series resistor here, which I'm assuming is not a short. Yeah, these are fine. This is a short, I guess. Let me see. Oh, that's I'm measuring across two terminals here. Never mind. So this is fine, but this is not a short. That's good. So it seems like this transistor has completely died. Now here's the problem. These three power supplies are all identical. If I were to change these, I would want to change them with something exactly the same or same transistor, because if you connect these power supplies in parallel to each other, they have to self-balance somehow. And I wonder if this is what this is for. I wish there was some kind of a data sheet or a manual for this, but either way, first thing first, we got to remove this, replace it with something equivalent or at least the same one. We got to replace all of these resistors, and we have to clean this because sometimes these things are conductive because it's a burst of carbon explosion, and these can become conductive surfaces. You don't want that, even though they're across very tiny resistors. You just don't want that around the circuit. So yeah, the fuse did not do anything, obviously, so these resistors exploded instead. Let's go ahead and find out what kind of device this is. So I didn't have the patience to wait for a whole digi-key order, so I just removed one of the other DL resistors I had, and I reconfigured its pins and put shrink tube and make sure it's nicely insulated and glued it right onto the board. So this is now connected. This should provide us with a soft start that we wanted to do. So this, I believe, is now a functioning unit. Now for the other one, I did have a transistor to replace, so that part was straightforward. I replaced the transistor already, but what I didn't have are these resistors here. So if you look carefully, you can see that I kind of hacked together a couple of resistors in parallel to kind of roughly reach the value that was there. It's not precise, but I don't think it matters. I don't believe these are sense resistors. I think they're just for protection. I hope so, at least. Based on what I've seen, I don't think that's going to be an issue. And that's it. The sense resistors are here. These are sense resistors for measuring how much current is going. You can see two sense lines coming out of them and going into this controller section. So other than that, I think this looks good. So let's close it back up and hook it up. And I think this power supply can be powered with only one of the modules installed. So let's go with that. So here's how I put it back together. I'm using the two boards that I repaired, one over here and one on the other side, and the controller board is directly on top of it. You can see I've connected the crossbars, which would be normally the output of the instrument, and I'm feeding it back to the sense so that the sense amplifier is actually engaged and can stabilize the voltage. And other than that, the other two sides are completely empty. I'm just looking at the voltages with the multimeter to see if it does anything weird. Right now the multimeter is just basically reading nothing. Let me get the glare out of the way. Yeah, so it's just reading minus 1.2 volts. So let's go ahead and turn it on and see if anything happens. Here we go. So I'm going to fix the camera one more time. And the power on. Let me stand back in case of explosions. And, ooh, there's some light. Ah, there we go. That is promising. Look at that. Power on. It's doing some kind of self-test. And, whoa, that's a lot of voltage. 80 volts. Oh, but look at that. It's actually doing 80 volts. Right there at the very far back, if you can see. So it is generating the right voltage. That's promising. I should be able to turn it off. And yes, it's actually doing a read. So set. Okay, it's set to 81. Let's lower it. Let's set it to 10 volts. And there you go. It went to 10 volts. And it's actually, this is a readout. You can see this blinking because of my camera shutter speed. But anyway, turn it off. Goes to 0. And indeed, I'm reading 10 volts. There it is. So that's really good. Now the question is, what happens when I put it all back together in the presence of the other modules? And I think this potentiometer here is probably for calibration purposes. But let me just put it back together like this because I think it's very, very good already. It's reporting very close to what the front panel says. Well, one more step. All right, and here it is back together again. I'm very eager to test it. I closed the sense port and all the screws exactly as they were before. I lost one of the black ones, so I'm using a zip tie here. Other than that, I think it looks pretty good. Now let's put the case on, see if we can get anything out of it. Okay, here we go. I have the GW Instek PSW80 connected directly to my BK Precision 8601 electronic load. So first, when the electronic load is not enabled, we can use this as a 6.5 digit multimeter. It's an excellent multimeter as well. So let's go ahead and try that. We're going to turn it on, and it should go through some kind of a self-test. Let's see. So power on. Now remember, all three modules are in there. They're all in parallel, so these things have to now work together. So every circuitry should be now engaged. And I checked the fans, and all three of them are running. So all three modules are functional. Well, let's go ahead and dissipate some current, and let's see what happens. Actually, first, let's see what is it set to. So it is set to 0 volts and 3 amps. The output is enabled when it turns on. That's not good. There must be a way to disable it. It's probably so when it powers on in case of a power failure. that it would come back and start providing power again perhaps. But so 0 seems to be very good, 0.00, same as that. Let's set it to some voltage. So I can actually directly change it from here. Let's go to 1 volt, let's see. There we go, 1 volt, 1.00, 1.00. It's a good match, no current being drawn. Everything seems to be good and synchronized to each other internally. Let's go to 5. There's 5 volts, 5.00, 5.00. It's very accurate actually. It must have a very good calibration still. So let's go higher. Let's try 20 volts. 19.99. There we go, 19.99. Very good. This should go to 80 volts. Let's just go crazy. Go as high as it can go. There it is, 83.95, 83.98. So it's a few digits here higher on this one, but it seems to be working really well. So right now, let's go back actually to something reasonable, maybe 15 volts. And actually, it works. I think it has acceleration built into it too. So here's 15 volts, 14.99. So it looks good. Now, what is our current limit? Our current limit is 3 amps. So if I try to take 2 amps from it, it should work no problem. There you go. There it is. 2 amps would be about 30 watts. It is drawing exactly 2 amps here. So it seems to be working under load. Now, at 2 amps, this guy is still in CV mode, it's continuous voltage mode, hasn't gotten constant current volt, or constant voltage, I should say. I want to bring it into constant current. Now, this limit is set to 3 amps. Now, if I set this to 3 amps, I might be able to get them into a runaway situation with respect to each other, because this will demand 3, is right at the edge. The voltage may fall, this will still demand 3, and the voltage will continue to fall, and it may go down like a linear ramp and collapse. Let's see if that happens. There you go, let's see. It might happen. There it is. It's beginning to happen. There you can see now it's going to collapse. This is what happens when 2 feedback networks are in a row like this. There you go. It's going to continue to demand more and more. It's going to collapse. It should bring this down to essentially almost 0. So this is a good test. It means that it's right at the edge. It's working. It continues to demand more and more. And yep, it collapsed as no surprise. So if I go ahead under set and I increase this by a little bit, let's go to 4 amps, it should immediately recover, and it does. Perfect. It looks very good. If I turn it off and then turn it on, yep, no problem. It recovers without any issues. We can try and take more current from it. Let's say that we we start providing, let's say 50 volts. Let's go to 50 volts. There it was. That's 50 volts, 150 watts being dissipated. No problem, this thing can go to 250 watt. Obviously, this doesn't fully test this. There's a lot of other things to still test. We have to make sure that we go through all the diagnostics, make sure it turns on and off correctly. Do all those things to do the correctly tested, make sure it doesn't overshoot and it doesn't go over temperature. We have to check the transient, make sure everything's working. But I don't see why it wouldn't be. I think it is repaired, and it's going to be a nice power supply on the bench if we do any really high power applications. For example, charging very high voltage supercapacitors, things like that. This is an excellent power supply, especially because it goes to 80 volts. And well, there you have it. I hope you enjoyed this quick, simple repair. And again, thank you so much for my Patreon supporters. In the next video, I will announce the winner of the oscilloscope that I'm giving away, and there's going to be pretty much one every month. So it's going to be great, at least for some time. So let me know what you think about the video, and I'll see you in the comment section.